Today I am going to be dissecting this DC motor that came out of a Honda fuel pump and then measuring its speed using a tachometer. Why would you want to do that? Well, let me explain. In the video I made on the Honda electric fuel pump diagnostics, I showed how a technician often uses the current ripple pattern to measure the motor speed. But after I published that video, my buddy Dave texted me and said, "Are you sure the speed of that fuel pump was really 5,000 RPM? Maybe it was 2,500 RPM. And here's what he was thinking. As the motor goes through its first half revolution, it goes through every set of commutator segments. And then in the next half revolution, it goes back through those same segments, just with the opposite polarity. But you'd think that second half revolution electrically might look identical to the first half revolution. If that's true, then the repeating pattern we saw in the current waveform might actually correspond to a half revolution, not a full revolution, in which case the motor speed would be half what we thought it was. So he's a sharp guy, so I said, "I'm not sure I know the answer to your question. I do know Picoscope recommends doing it this way, and a lot of technicians seem to do it this way. But I'll tell you one thing for sure. By the time we get to the end of this video, we'll know the answer." Here's a little animation I put together to illustrate how a DC motor works and also the question at hand. This is the commutator ring for the motor. And in a DC motor, the wind-ins are a continuous set of wind-ins that connect all around in a loop and then are just contacted by the commutator as shown. So as the armature rotates around, the brushes are just contacting different points on that continuous wind-in loop. There's a brush on one side of the armature and on the other side to supply power to the armature. With the armature positioned as shown, the brushes are actually shorting out two adjacent commutator segments. So in this position, the current comes in, goes through three wind-ins and out through the other brush, and also goes through three wind-ins shown on the top here and out through the brush. But notice that these two wind-ins actually aren't used at all in the current armature position because they're shorted by the brush that's contacting both commutator segments. If we rotate the motor back one half commutator segment, now the current comes in and goes through four separate wind-ins and out the other brush, and the current goes through four wind-ins on the top and out through the brush. So in this case, because the current is going through four wind-ins rather than three on each side, the resistance is going to be higher and the current will be lower. So we'll expect that whenever the brushes are perfectly centered on a commutator segment, the current should be lower. And when the brushes are shorting out adjacent commutator segments, then the current will be higher. So as the armature rotates and the commutator ring rotates along with it, as we go from being centered on the commutator segment to shorten adjacent commutator segments, we expect the motor current to increase slightly. And then as we rotate onto the next commutator segment, we expect the current to drop back down. And in this fashion, as the motor rotates around and makes a full revolution, we expect a little ripple of current each time the brushes go to the next commutator segment. And due to slight differences in resistance of how the brush contacts each commutator segment, the resistance of the commutator segment, and the winding resistance differences, we expect that there will be a little variation between the current ripple for each of those segments. So typically we expect that for one rotation, we'll get some identifiable repeating sequence of ripple. And from that period, we can determine the period of revolution for the motor and therefore the motor speed. So now here is the question. We know that as the motor rotates through its first half revolution, we will get four bumps of current as the brushes cross over each commutator segment. But the question is, now we're back at exactly opposite of where we started, but energizing exactly the same contacts on the commutator. We started energizing contacts 1 and 5 and then switched to 2 and 6. And now we're at 5 and 1, and the next set will be 6 and 2. So it's the same sequence of contacts that will be energized in the next half revolution as the first half revolution, just with the opposite polarity. So the question is, as we rotate through that next half revolution, do the 4 current pulses that we get mirror exactly the first 4 current pulses, because electrically it seems to be the same circuit. And if that's the case, then the length of the repeating sequence that we observe in the motor current ripple is actually half the period of rotation, not the full period of rotation of the motor. So now let's go find out what the real story is. Okay, so to get to the bottom of this, we're going to take the motor, run it at 12.8 volts, and then I've got a tachometer set up here. I've got a little piece of reflective tape there, so it'll be able to count the RPMs and display them up there. Sorry, it's upside down. I've also got the picoscope here, and at the same time I'm going to capture the waveforms on the oscilloscope, and then we'll compare the speed we get with the tachometer to the oscilloscope method. So here goes. So it looks like it was 69.77 RPMs on the tachometer. Let's go see what the scope says. Okay, so let's just go back a few frames of data to get nice uniform data. And then we'll put our cursors on one of those repeating patterns. You can see this large spike every 8 cycles. So let's measure that period. And then you can see down here it's 6,970 RPM. So in very close agreement with the tachometer reading. So I think that's good confirmation of the fact that the repeating cycle is one full rotation of the pump, and the method we were using originally is accurate, it seems. So just for fun, let's try doing it at a lower voltage, maybe 10.2 volts or so, and see how the speed compares and see if it still lines up with both measurement methods. So it looked like that was about 54.37 RPM on the tachometer. Let's go see what the scope says. Okay, so let me just go back a few frames and get some nice clean data, and then we'll line up on that repeating sequence again. And then it looks like the speed, according to the current ripple waveform, is 54.27 RPM, which is really close to what we measured with the tachometer, which was 54.37 or so. So I think this really does validate the method of using the current ripple, and it does seem like the unique pattern, repeating pattern of ripple does correspond, at least on this motor, to a full revolution of the motor. So our previous experiment showed that the current ripple waveform is truly unique across a full revolution of the motor, even though the contacts are repeated. It's hard to say why that's true, or even if it's true across all motors. But one possibility is that the brush fitment plays a role in the overall resistance. For example, if you picture that maybe contact 1 has worn a weird kind of protrusion here, I've exaggerated it just to make the point, and maybe the brush on the left side has worn to fit that protrusion well, but the brush on the right side is more in its factory original form. Well, in this case, clearly, as we rotate the motor around 180 degrees, even though we're trying to energize the same contacts just in reverse polarity, the fitment of the brushes now is very poor, so we might expect the resistance to be much higher. So perhaps the fitment of the brushes is a big reason why there's this asymmetry, but perhaps there's other reasons that I don't know of as well. I'd love to hear if you have some thoughts on the matter. So now I thought it might be just of interest to some people to tear the pump apart the rest of the way and just see what's inside. These are the vanes here that do the actual pumping, and originally it had this end cap on it, and this is the inlet for the fuel, and then it had this plastic assembly on it. And so normally this whole assembly would sit like that in your tank, and this is the fuel filter here, and then this gets inserted into this fuel pump assembly. So on the top end here you can see the commutator, and as we expected, it does have 8 segments. It's 1, 2, 3, 4 on the top, 5, 6, 7, 8 on the bottom there. And then it did have this brush assembly, and the brushes just come in here and sit on top of the commutator ring and wipe around in a circle. So you might wonder where the fuel inlet is on the bottom of the pump. Where does the fuel come out? So that the vanes just pop out and all of the fuel gets pumped up through that little hole. And in these fuel pumps, the fuel is actually constantly running through the inside of the motor up around the armature. In this whole area with the brushes and everything is filled with fuel. And then the fuel actually gets pumped out through that little hole in the top, up through the check valve here, and then out this outlet. And that's okay because gasoline, turns out, is a good insulator, so it doesn't bother anything electrically, and that's what provides cooling for the motor. So we can pull the armature out here, and you can see the armature is kind of has this plastic sealing around it, and I think that's probably just to reduce turbulence so that it's a smoother surface around. As it spins around, it won't agitate the gasoline that's going up around it as much, as my guess. So it's kind of interesting that the fuel is constantly running through the inside of the fuel pump. So I learned a lot putting that video together. I hope you found it interesting, and thanks a lot to my friend Dave for the great question, and thanks to you for watching. So I thought of one more thing that might be interesting to try, and that is to rotate the motor around and measure the resistance through the motor as the brushes go through a full cycle. So I've got the armature set up with the brushes here in a vise just to hold it together, and you can see the brush coming down there, and right now it's, let me get it. So right now it's centered on one of the commutator segments, and then now it's overlapping between segments and onto the next segment. So I'm just going to measure it on every contact and every overlap of two contacts all the way around in a full cycle, and then I'll share the results with you after. I got permission from work to borrow a nice benchtop meter, which has a lot more precision to measure the resistance more accurately. So right now I've got it lined up so that the brushes are centered on the commutator segment, and you can see it's measuring 0.810 ohms, and now I'm going to rotate the armature around so the brushes are short into adjacent contacts, and you can see the resistance drop to 0.72 ohms or so. So as expected, when the brushes are shorting out adjacent contacts and it's shorting out that winding, the resistance does drop as we expected. So now I'm going to go around and just measure the resistance in a full rotation of the motor, and I'll share the results with you after. This graph shows the resistance of the motor across a full revolution of the motor, and I've repeated the measurements twice just to see how repeatable they were. And you can see that there are some slight discrepancies between the two sets of measurement, probably because I didn't line up the brushes in exactly the same spot each time. But you can see that the overall trend is that the resistance is highest when the brushes are lined up perfectly on a commutator segment, and then each time the brushes overlap to the next commutator segment, the resistance drops. And there are differences in resistances all through the period of rotation. This graph shows the resistance through the first half revolution of the motor compared to through the second half revolution in orange. And you can see there is a clear difference in the resistance between the first half revolution and the second half revolution. Finally, this graph just shows the motor resistance over multiple rotations of the motor, and you can see that there clearly is a pattern that repeats every 8 ripple segments as expected.